Did you know that right now, as you listen to these words, you're being bombarded by trillions of particles that have traveled 93 million miles through empty space? These particles, photons of sunlight, are colliding with your skin, your clothes, and everything around you at a speed of 186,000 miles per second. And here's the most impressive part. Each of these photons began their journey in the sun's core about 100,000 years ago, struggling to escape the extreme density of our star before finally traveling through space to reach you. But this isn't just a fascinating astronomical curiosity. These photons touching you right now are literally the architects of our planet's climate. They heat the oceans, move air masses, evaporate the water that forms clouds, and drive every wind that blows. Without them, Earth would be a frozen ball of rock floating in the void, with temperatures of minus 430 degrees Fahrenheit. Hello and welcome to an exploration of one of the most powerful forces shaping our existence, the sun's influence on Earth's climate. I'm here to guide you through a journey that will reveal how our central star is not just a source of light and heat, but the grand conductor of a complex climatic symphony that plays endlessly on our planet. You've probably heard people talk about the sun warming our planet, but the reality is infinitely more sophisticated and beautiful than that simple statement suggests. The sun doesn't just heat the Earth, it choreographs every aspect of our weather and climate systems. From the formation of a single cloud to the massive ocean currents that redistribute heat around the globe, from the seasonal rhythms that govern life cycles to the long-term climate patterns that shape civilizations, everything traces back to our relationship with our star. Have you ever wondered why we have seasons? Or why the wind blows? Why some regions are deserts while others are rainforests? Why the weather changes from day to day? The answer to all these questions lies in understanding how solar energy interacts with our planet's atmosphere, oceans and land surfaces in ways that are both elegantly simple and bewilderingly complex. Tonight, we're going to unravel this cosmic relationship together. We'll discover how solar radiation creates weather patterns, how tiny variations in the sun's activity can influence global climate, and how our growing understanding of these processes is reshaping how we think about our planet's future. We'll explore how ancient ice sheets and modern solar panels are both responses to the same stellar energy, and how the dance between our star and our world connects every living thing on Earth. Imagine for a moment that you're a photon of light born in the nuclear furnace at the sun's core. You begin your existence in a region where temperatures reach 27 million degrees Fahrenheit, and the pressure is 250 billion times greater than Earth's atmospheric pressure. You're created when 4 hydrogen nuclei fuse together to form one helium nucleus, releasing a tiny amount of energy, but you're just one of an incomprehensible number of photons being born every second in this stellar factory. Your journey to reach us here on Earth is an epic odyssey that spans both space and time. For tens of thousands of years, you bounce randomly through the dense interior of the sun, absorbed and re-emitted countless times by particles in the stellar plasma. It's like trying to escape from the world's most crowded room, where every step you take is blocked by someone else. Eventually, after this incredibly long journey through the sun's interior, you finally break free from the surface and begin racing through space at the speed of light. 8.5 minutes later, you arrive at Earth's atmosphere, but your work is far from over. Depending on your wavelength and energy, you might be absorbed by water vapor in the air, reflected by clouds, scattered by tiny particles, or make it all the way to the surface where you could warm a rock, power photosynthesis in a leaf, or even be captured by a solar panel to generate electricity. This is the story not just of a single photon, but of the countless trillions of photons that create weather, drive climate, and sustain life on our planet. And the question that will guide us through this journey is both simple and profound. How exactly does this star, 93 million miles away, manage to control everything from the formation of a cloud above your head to the great climate patterns that define entire civilizations? The answer, my dear companion, is both more complex and more beautiful than you might imagine. And as we begin to unravel it, you may never look at a ray of sunlight the same way again. Let's begin our exploration by getting to know our solar protagonist better. The sun isn't just a giant light bulb hanging in the sky. It's a thermonuclear power plant of unimaginable proportions, where every second, 600 million tons of hydrogen transform into helium through nuclear fusion. To give you an idea of this magnitude, it's as if 91 billion hydrogen bombs exploded in the solar core every second. And all this energy begins an epic journey that will eventually end up touching your skin. When we think about the sun influencing our climate, it's easy to imagine just the heat we feel on a sunny day. But the reality is infinitely more sophisticated. The sun emits energy across the entire electromagnetic spectrum, from radio waves to gamma rays. Each type of radiation interacts differently with our atmosphere, creating a complex tapestry of climatic effects. Visible light, the kind that allows you to see these words, represents only about 44% of the solar energy that reaches Earth. The remaining 56% is divided between infrared radiation, which we feel as heat, and ultraviolet radiation, which tans our skin and drives crucial chemical reactions in the upper atmosphere. Have you ever wondered why the sky is blue? It's because molecules in our atmosphere scatter blue light more than other colors. And this same scattering of sunlight is one of many mechanisms by which our star shapes Earth's climate. But here's something fascinating. Not all solar energy that leaves the sun reaches us. In fact, Earth intercepts only a tiny fraction, about 1/billionth of all the energy the sun produces. Even so, this small amount is equivalent to about 174 petawatts, or roughly 10,000 times more energy than all of humanity currently consumes. Imagine for a moment this energy as a golden river of light and heat flowing through space. When this river encounters our atmosphere, something magical happens. It begins to be filtered, reflected, absorbed, and redistributed in ways that create all the climate phenomena we know. Clouds form, winds blow, rains fall, and even the oceans circulate, all orchestrated by energy from our star. And there's yet another fascinating aspect. The sun is not constant. It pulses, varies, and changes in cycles that can last days, years, or even millennia. These solar variations, however small, can trigger significant changes in our climate. It's as if our star were a conductor who sometimes speeds up the tempo of the music, sometimes slows it down, creating different movements in our planet's climatic symphony. Did you know that the sun has its own atmosphere? The solar corona, which we can only see during total eclipses, extends millions of miles into space and occasionally spits material in our direction through coronal mass ejections. When this material hits Earth, it can cause everything from the beautiful northern lights to interference with satellites and power grids. But more importantly, these solar storms can subtly influence our planet's climate patterns. So while you're sitting there, breathing calmly, remember, every molecule of oxygen in your lungs was released by plants that used solar energy for photosynthesis. The heat warming your body comes from the sun's infrared radiation. And even Earth's movement that generates the seasons is a cosmic dance with our central star. The sun's energy doesn't just warm our planet randomly. Solar radiation heats the equatorial regions more intensely than the polar regions, creating temperature gradients that drive all atmospheric and oceanic circulation on our planet. It's as if the sun were the heart of a vast thermal engine, pumping energy that spreads through air and water currents across the entire globe. You've probably noticed that it's warmer during the day than at night, warmer in summer than winter. These seem like obvious observations, but they represent fundamental aspects of how solar energy shapes our climate. The daily cycle of heating and cooling creates local wind patterns. The seasonal cycle drives global weather systems. And longer-term variations in solar energy can influence climate patterns that last for decades or centuries. But the sun's influence goes beyond just temperature. Solar energy drives the water cycle that brings us rain. It powers the photosynthesis that produces the oxygen we breathe and removes carbon dioxide from the atmosphere. It creates the atmospheric circulation patterns that transport heat from the tropics to the poles, moderating global temperatures. Every process we associate with weather and climate, evaporation, condensation, precipitation, wind formation, ocean currents, can be traced back to energy from our star. The sun is not just a source of energy. It's the fundamental driver of all dynamic processes in our climate system. And here's something that might surprise you. The relationship between solar energy and Earth's climate is not static. It's constantly evolving as our planet's atmosphere, oceans, and land surfaces change. Ice sheets grow and shrink, affecting how much sunlight is reflected back to space. Forests expand and contract, changing how much solar energy is absorbed versus reflected. Volcanic eruptions can temporarily alter how much solar energy reaches the surface. This dynamic relationship between our star and our planet has been ongoing for billions of years, creating the conditions that allow life to exist and thrive on Earth. Understanding this relationship is key to understanding not just how our climate works today, but how it might change in the future. Now, my dear listener, let's delve into one of the most poetic and scientifically elegant aspects of our story: how our atmosphere transforms the raw energy of the sun into something that can sustain life. Imagine Earth's atmosphere as a translucent veil of multiple layers, each with its own personality and function, floating gently around our planet. When solar radiation hits the top of our atmosphere, it first encounters the thermosphere, where temperatures can reach over 1,800 degrees Fahrenheit due to the absorption of the most energetic ultraviolet radiation. It's here that one of the first acts of transformation occurs. Oxygen and nitrogen molecules absorb and fragment the most dangerous UV radiation, protecting life on the surface. Have you ever thought that you're constantly being protected by an invisible shield working tirelessly above your head? Descending a bit, we reach the mesosphere, where meteors from space disintegrate into luminous streaks that we sometimes see as shooting stars. But it's in the stratosphere that we find one of the most important characters in our climate story: the ozone layer. This ozone, formed when ultraviolet radiation from the sun breaks apart oxygen molecules and recombines them differently, acts as a selective filter, allowing visible light and infrared radiation to pass through while blocking much of the harmful UV radiation. And then we reach the troposphere, our most intimate atmospheric layer, where we live and where virtually all the weather we experience happens. It's here that solar energy truly transforms into weather. Solar radiation heats Earth's surface unevenly, more in the tropics. Less at the poles, more on land than on oceans, more during the day than at night. These temperature differences create pressure differences, and pressure differences create movement, wind. But did you know that only about 23% of the solar energy entering Earth's atmosphere reaches the surface directly without being modified? The rest is absorbed by atmospheric gases, reflected by clouds, or scattered by particles in suspension. Each of these processes contributes to the complex energy balance that determines our climate. Think of the atmosphere as a great chemical laboratory where solar energy catalyzes countless reactions. In the stratosphere, for example, UV radiation creates ozone, but it can also destroy it when it encounters certain pollutants. In the troposphere, sunlight triggers photochemical reactions that can form both the oxygen we breathe and the smog that sometimes chokes our cities. There's something almost poetic about how our atmosphere breathes. During the day, it absorbs solar energy and expands slightly. During the night, it contracts as it radiates this energy back to space. This daily rhythm of expansion and contraction contributes to local wind patterns that you might feel as an evening breeze or the calm of dawn. And what about clouds? These floating sculptures of water vapor are perhaps the most visible manifestation of solar influence on our climate. The sun evaporates water from oceans, rivers, and lakes. This vapor rises, cools, condenses into tiny droplets around particles of dust or salt, and forms clouds. But clouds aren't just a consequence of solar energy, they also modify it, reflecting part of the radiation back to space and trapping part of the heat near the surface. It's a feedback system as elegant as it is complex. More solar energy creates more clouds, which can reflect more solar energy, cooling the surface. But these same clouds can also act like blankets, keeping heat near Earth during the night. The atmosphere is literally a living system that breathes, pulses, and constantly adapts to the energy it receives from our star. The atmosphere also acts as a giant optical instrument, bending and scattering sunlight in ways that create phenomena like rainbows, sunsets, and the blue sky. When sunlight hits tiny water droplets in the air just right, it separates into all the colors of the spectrum, creating a rainbow. When the sun is low on the horizon, its light has to travel through more atmosphere, scattering away the blue light and leaving the warm reds and oranges of sunset. But beyond these beautiful visual effects, the atmosphere's interaction with solar radiation has profound implications for climate. Different gases in the atmosphere have different wavelengths of solar radiation. Water vapor absorbs infrared radiation, contributing to the greenhouse effect. Ozone absorbs ultraviolet radiation, protecting the surface but also heating the stratosphere. Carbon dioxide absorbs both infrared radiation coming from the sun and infrared radiation emitted by Earth's surface. These selective absorption processes mean that small changes in atmospheric composition can have large effects on climate. Adding more greenhouse gases to the atmosphere enhances its ability to trap heat. Reducing ozone in the stratosphere allows more harmful UV radiation to reach the surface. The atmosphere is exquisitely sensitive to changes in both the solar energy it receives and its own chemical composition. And here's something remarkable. The atmosphere doesn't just passively filter solar energy, it actively redistributes it around the planet. Hot air rises at the equator and flows toward the poles at high altitude, while cool air flows back toward the equator near the surface. This creates the great circulation cells that drive global wind patterns and weather systems. Without this atmospheric circulation driven by solar energy, the tropics would be unbearably hot and the poles would be even colder than they are now. The atmosphere acts as a great heat engine, using solar energy to transport warmth from regions that receive excess energy to regions that receive too little, moderating temperatures across the globe and making our planet more hospitable to life. Take a deep breath again, my dear travel companion. Feel the air entering and leaving your lungs. This simple act is part of a global energy balance so precise and delicate that it connects you to all other living beings on the planet, and all of us to our central star. Earth, seen from space, is a predominantly blue sphere that constantly receives energy from the sun and constantly loses energy to space. For our planet to maintain a stable average temperature over time, the energy coming in must equal the energy going out. It's like a cosmic bank account that needs to stay balanced at all times. Of the 174 petawatts of solar energy that reach the top of our atmosphere, about 30% are immediately reflected back to space by the atmosphere, clouds, and Earth's surface. This phenomenon has a poetic name, albedo, from the Latin word for whiteness. Different surfaces have different albedos. Fresh snow can reflect up to 90% of the sunlight it receives, which is why you need sunglasses on a sunny day in the snow. A calm ocean, on the other hand, can absorb more than 95% of solar radiation, which is why deep waters appear so dark. The remaining 70% of solar energy is absorbed by the Earth-atmosphere system. Part is absorbed directly by the atmosphere, but the largest portion heats Earth's surface, the continents, oceans, glaciers, and forests. And here's where something fascinating happens. This absorbed energy doesn't stay put. It transforms and moves. Imagine Earth as an immense heat engine. Solar energy heats equatorial regions more intensely than polar regions, creating temperature gradients that drive all atmospheric and oceanic circulation on the planet. It's as if the sun were the heart of this engine, pumping energy that spreads through air and water currents throughout the globe. Have you ever wondered why we have wines? The answer lies in this purposeful energy imbalance that the sun creates. Warm air, being less dense, rises in equatorial regions, creating areas of low pressure. This air travels toward the poles in the upper layers of the atmosphere, cools, descends, and returns to the tropics near the surface. If Earth didn't rotate, we would have just two large circulation cells. But because our planet spins, this circulation breaks into 6 distinct cells, creating the wind patterns we know, the trade winds, westerlies, and polar winds. But solar energy doesn't move only through air. The oceans, which cover more than 70% of Earth's surface, are immense reservoirs and transporters of solar energy. Water has a very high heat capacity, meaning it can absorb and store enormous amounts of thermal energy. Ocean currents function like planetary conveyor belts, transporting water heated by the sun from the tropics toward the poles and bringing cooler water back. The Gulf Stream, for example, carries tropical water heated by the Caribbean sun to Western Europe, keeping countries like England with a milder climate than their latitude would suggest. Without this ocean current fed by solar energy, London would have a climate similar to Labrador, Canada. And there's yet another magical aspect: evaporation. When the sun heats the oceans, part of the water transforms into vapor and rises into the atmosphere, carrying with it not just H2O molecules, but also energy in the form of latent heat. When this vapor condenses into clouds or precipitation, it releases this energy, heating the surrounding air. That's why tropical regions where there's lots of evaporation have such energetic rainfall. All this movement of energy, through winds, ocean currents, evaporation, and precipitation, is a constant attempt by Earth to balance the excess energy it receives in the tropics with the deficit it experiences at the poles. It's a perpetual dance between heat and cold, between what rises and what falls, between what evaporates and what condenses. You're participating in this dance right now. The heat from your body is constantly being lost to the environment, part of the energy you obtained from food, which in turn obtained energy from the sun through photosynthesis. You are literally a small human sun, transforming stored solar energy and radiating heat to the world around you. This energy balance is maintained through incredibly complex feedback mechanisms. When more solar energy is absorbed, more water evaporates, creating more clouds. More clouds can reflect more solar energy back to space, cooling the surface. But these same clouds can also trap heat near Earth's surface, warming it. The net effect depends on the type, altitude, and thickness of the clouds. Similarly, when regions become warmer, ice melts, exposing darker surfaces that absorb more solar energy, leading to more warming. When regions become cooler, more ice forms, creating brighter surfaces that reflect more solar energy, leading to more cooling. These feedback loops can either amplify or dampen changes in Earth's energy balance. The atmosphere and oceans work together to maintain this energy balance through what scientists call the global heat transport system. Warm, moist air rises in the tropics, carrying energy upward. This air flows toward the poles at high altitude, gradually cooling and sinking. Meanwhile, ocean currents transport warm water poleward near the surface and return cold water toward the equator at depth. This system is so efficient that despite receiving very different amounts of solar energy at different latitudes, Earth's temperature differences between equator and poles are much smaller than they would be without atmospheric and oceanic heat transport. It's a planetary air conditioning system powered entirely by solar energy. And here's something that might surprise you. This energy balance has remained remarkably stable over Earth's history. Despite significant changes in solar output, atmospheric composition, and surface conditions. It's this stability that has allowed life to evolve and thrive on our planet for billions of years. Understanding Earth's energy balance is crucial for understanding climate change. Any factor that changes how much solar energy Earth receives, how much it reflects back to space, or how efficiently it redistributes energy around the globe can alter this balance and change our climate. The delicate equilibrium between incoming solar energy and outgoing terrestrial radiation is what maintains the conditions that make our planet habitable. Now, my dear listener, let's embark on one of the most beautiful demonstrations of how cosmic geometry transforms into climatic poetry. Do you know why we have seasons? The answer might seem obvious because Earth moves away from and closer to the sun, but that's not the truth. The reality is much more elegant and surprising. Our Earth is not a ballerina dancing upright around the sun. It's tilted, like a giant spinning top in space with a slight inclination of 23.5 degrees relative to the plane of its orbit. This tilt, which scientists call obliquity, is the true creator of the seasons. Imagine, for a moment, that you're floating in space, watching Earth on its annual journey around the sun. During half the year, the northern hemisphere is slightly tilted toward the sun, receiving more direct solar rays, and for more hours per day, it's our summer. During this same period, the southern hemisphere is tilted away from the sun, receiving more oblique solar radiation, and for less time, it's the austral winter. 6 months later, the situation completely reverses. Now it's the southern hemisphere that tilts toward the sun, experiencing its summer, while the north tilts away, plunging into winter. And twice a year at the equinoxes, Earth finds itself in a position where both hemispheres receive equal amounts of solar radiation. These are the brief moments of global balance. Have you ever stopped to think about the mathematical beauty of this? The difference between summer and winter isn't a question of proximity to the sun, but rather of angle. During winter in the northern hemisphere, Earth is actually at its closest point to the sun, perihelion. But the solar rays arrive so obliquely that they can barely warm the surface. It's like the difference between shining a flashlight directly on your hand versus shining it at an angle. The same amount of light spreads over a larger area when tilted, decreasing its intensity per square meter. This is exactly the physical principle that governs the seasons. But there are more layers to this story. Earth's tilt is not fixed in time. It slowly oscillates between 22.1 and 24.5 degrees over a cycle of approximately 41,000 years, called the obliquity cycle. When the tilt is greater, seasons are more extreme, hotter summers and colder winters. When it's smaller, seasons are milder. This oscillation in obliquity is one of the components of the so-called Milankovitch cycles, proposed by Serbian mathematician Milutin Milankovic in the early 20th century. These astronomical cycles, which also include changes in Earth's orbital eccentricity and axial precession, modulate the amount and distribution of solar radiation that Earth receives over tens of thousands of years. Have you ever wondered how our ancestors explained the seasons before understanding astronomy? Many cultures created poetic myths, Persephone being kidnapped by Hades and cyclically returning to the surface, or the sun being periodically swallowed by a cosmic serpent. These stories, while not scientifically accurate, captured a deeper truth, the cyclical nature of seasonal climate changes. And what impact do these seasons have on global climate? During summer in the northern hemisphere, where most of the planet's landmass is concentrated, more solar energy is absorbed by land than during winter. This creates an annual modulation in Earth's global energy balance. It's partly why atmospheric CO2 concentrations oscillate seasonally during the boreal summer. The vast forests of the northern hemisphere absorb more carbon through photosynthesis intensified by greater solar energy availability. Seasons also drive the great monsoon systems that feed billions of people. When the Asian continent heats up during summer, it creates a low-pressure zone that sucks moist air from the Indian Ocean, bringing monsoon rains that are vital for agriculture. In winter, the pattern reverses, and dry winds blow from the continent toward the ocean. The seasonal cycle also affects ocean circulation patterns. During summer, increased solar heating of surface waters enhances evaporation and can strengthen or weaken ocean currents. During winter, cooling of surface waters can enhance deep water formation in polar regions, driving the global ocean circulation system that helps regulate Earth's climate. Even the length of days and nights varies seasonally due to Earth's tilt. During summer solstice in the northern hemisphere, the North Pole experiences 24 hours of daylight, while the South Pole experiences 24 hours of darkness. This extreme variation in daylight hours affects everything from plant growth to animal behavior to human circadian rhythms. The seasonal variation in solar energy also affects atmospheric chemistry. During summer, increased UV radiation enhances photochemical reactions that produce ozone in the troposphere and affect the ozone layer in the stratosphere. During winter, reduced sunlight slows these reactions, leading to seasonal variations in atmospheric composition. And here's something fascinating. The seasons aren't exactly the same length. Because Earth's orbit is slightly elliptical and our planet moves faster when it's closer to the sun, the seasons in the northern hemisphere are slightly different lengths than those in the southern hemisphere. Northern spring and summer are a few days longer than southern spring and summer. So the next time you feel the first cool breeze of autumn or the first warmth of spring, remember, you're feeling the geometry of the cosmos on your skin. You're experiencing, through your senses, the gravitational dance between Earth and the Sun, mediated by the precise angle at which our planetary tilt presents your region of the world to solar radiation. This cosmic choreography has been ongoing for billions of years, creating the seasonal rhythms that life on Earth has evolved to follow. From the migration patterns of birds to the flowering of plants to the hibernation of bears, countless biological processes are synchronized with this annual cycle of changing solar energy. We humans, too, are part of this cosmic dance, our lives shaped by the seasonal rhythms that connect us to the larger astronomical forces that govern our planet. My dear listener, up until now we've talked about the sun as if it were a constant and unchanging source of energy. But our star is much more dynamic and temperamental than that. The sun has moods, cycles, and even storms. And these variations, however subtle, can significantly influence our planet's climate. Have you ever heard of sunspots? They're not defects or dirt on our star's surface, but rather regions where the solar magnetic field is so intense that it inhibits convection, creating areas that are slightly cooler and therefore darker. What's fascinating is that the number of sunspots varies in a regular cycle of approximately 11 years, known as the solar cycle. During solar maximum, the sun's surface can be dotted with hundreds of sunspots, and solar activity is intense, with frequent solar flares and coronal mass ejections. During solar minimum, the surface can remain completely smooth for days or even weeks, and solar activity decreases dramatically. It's as if our star had periods of great agitation followed by periods of relative calm. Now, you might be wondering, what's the connection between these dark spots on the sun and the climate here on Earth? The answer is more complex and fascinating than you might imagine. During periods of high solar activity, the sun emits slightly more energy. The difference is only about 0.1%. But in terms of global climate, this can be significant. There's also intriguing historical evidence. The period between 1645 and 1715, known as the Maunder Minimum, was characterized by a virtual absence of sunspots. Coincidentally, this period corresponded to the peak of the so-called Little Ice Age in Europe, when extremely harsh winters froze the Thames River in London and allowed armies to march across frozen rivers in Holland. Was it just coincidence? Scientists still debate this question. Some argue that decreased solar activity during the Maunder Minimum contributed to regional cooling. Others suggest that particularly active volcanoes during this period may have been the main culprits. The truth, as often happens in climate science, probably involves a complex interaction between multiple factors. But solar variations aren't limited to the 11-year cycle. There are longer cycles, like the Gleisberg cycle of approximately 88 years, and even cycles that last centuries. These long-term variations in solar activity may be related to significant historical climate changes. For example, the period between the 10th and 13th centuries, known as the medieval warm period or medieval climate optimum, coincided with a period of high solar activity. It was during this time that Vikings managed to colonize Greenland and cultivate vineyards in southern England. Could the intensification of solar activity be one of the reasons for this regional warming? And there's yet another fascinating aspect. Solar flares and geomagnetic storms can influence cloud formation in Earth's atmosphere. When charged particles from the sun interact with our magnetosphere, they can generate cosmic rays that, in turn, can act as condensation nuclei for cloud formation. More clouds mean more reflection of solar radiation, potentially cooling the climate. This mechanism, proposed by Danish physicist Henrik Svensmark, suggests an almost poetic connection between our star's activity and the clouds dancing above our heads. Imagine, magnetic storms on the sun can literally sculpt the clouds in our sky. But it's important to maintain perspective. While solar variations can influence Earth's climate, they cannot alone explain the rapid climate changes we've observed in recent decades. Human influence on climate through greenhouse gas emissions is much more intense than any natural solar variation of the last few centuries. Still, understanding how the sun varies and how these variations affect our climate is crucial for completely understanding Earth's climate system. It's like trying to understand a symphony. You need to understand not just the main melody, but also all the harmonic variations that enrich it and make it complex. Have you ever observed a sunspot through a telescope with appropriate filter? They're often larger than Earth itself, true magnetic hurricanes on our star's surface. To think that these solar storms, happening 93 million miles away, can subtly influence whether we'll have more or fewer clouds above our heads is a powerful demonstration of the interconnectedness of the cosmos. Solar cycles also affect space weather, which can impact our increasingly technology-dependent society. During solar maximum, increased solar activity can disrupt satellite communications, GPS systems, and even power grids. The famous Carrington event of 1859 caused telegraph systems to fail worldwide and auroras to be seen as far south as the Caribbean. The solar cycle also affects the upper atmosphere's temperature and density, which can influence the orbits of satellites and the International Space Station. During solar maximum, increased heating of the upper atmosphere causes it to expand, increasing drag on orbiting objects. And here's something that might surprise you. Solar cycles may also affect Earth's ozone layer. During solar maximum, increased UV radiation enhances ozone production in the stratosphere, but can also enhance ozone destruction through photochemical reactions. These changes in the ozone layer can, in turn, affect atmospheric circulation patterns and potentially influence surface climate. Scientists are also studying potential connections between solar cycles and various Earth systems, from ocean circulation to atmospheric pressure patterns. While the mechanisms are not yet fully understood, there's growing evidence that solar variability can influence regional weather patterns through complex atmospheric and oceanic processes. Understanding solar variability is also important for climate prediction. If we can better predict how the sun's output will change over coming decades, we can better predict how Earth's climate might respond. Some scientists have suggested that solar activity might decline significantly in the coming decades, potentially moderating some of the warming expected from greenhouse gas emissions, though most studies suggest that even a significant solar decline would be insufficient to offset expected warming from human activities. Imagine, my dear cosmic travel companion, that you're sitting on a beach at sunset, watching waves rhythmically break on the sand. Suddenly, on the horizon, a giant wave forms that approaches majestically, carrying incomparable energy. This is an appropriate analogy for solar storms, magnetic explosions in our star's corona, that send waves of charged particles through the solar system. These storms aren't rare. Every moment you blink, small eruptions happen on the solar surface. But periodically, especially during solar maxima, truly spectacular events occur. Coronal mass ejections that can release in a matter of hours. The energy equivalent to billions of hydrogen bombs. When one of these solar storms is directed toward Earth, the consequences can be both beautiful and potentially disruptive. The charged particles, mainly protons and electrons, travel through space at speeds up to 1,200 miles per second. In 18 to 36 hours, they hit our magnetosphere, the invisible magnetic bubble that protects our planet. It's at this moment that one of nature's most dazzling spectacles occurs, the auroras. When solar particles interact with gases in our upper atmosphere, they cause oxygen and nitrogen atoms to glow like cosmic neon. Oxygen produces the green and red curtains that dance in polar skies, while nitrogen creates blue and violet hues. Have you ever wondered if, right now, someone somewhere near the Arctic or Antarctic is contemplating this dance of lights, a direct result of a storm on our star? But solar storms have effects that go far beyond the beauty of auroras. They can interfere with communication systems, affect satellites, and even cause blackouts in power grids. In 1989, a particularly intense geomagnetic storm left the entire province of Quebec, Canada, without electricity for 9 hours. And there's a more subtle and intriguing connection to climate. Solar storms can influence atmospheric circulation in the upper layers of the atmosphere. When energetic solar particles penetrate the polar stratosphere and mesosphere, they can alter the chemistry of this region, affecting ozone distribution and modifying atmospheric heating patterns. This altered heating at high latitudes can, in turn, influence global atmospheric circulation patterns. It's a fascinating domino effect. A magnetic explosion on the sun can, weeks later, influence wind patterns that determine whether you'll have a more severe or milder winter. There are studies suggesting that intense solar storms can even affect cloud formation through modulation of cosmic rays hitting our atmosphere. Normally, Earth is constantly bombarded by cosmic rays from deep space, high-energy particles that can act as condensation nuclei for cloud formation. During solar storms, the intensified solar wind can deflect some of these cosmic rays, potentially reducing cloud formation and allowing more solar radiation to reach the surface. It's a theory still under debate, but imagine the scientific poetry of it. Storms on our star can literally sculpt the clouds in our sky, determining whether we'll have a sunny or cloudy day. Historically, there are fascinating records of great solar storms. The Carrington event in 1859 was probably the largest geomagnetic storm recorded in the modern era. Auroras were seen even in the Caribbean, and telegraph systems failed worldwide. Some telegraph operators reported that they could send messages even with their equipment turned off. The atmosphere itself had become conductive due to the solar storm. If a similar event occurred today, the consequences would be much more dramatic. Our modern society depends intensively on satellites, GPS, internet, and sophisticated power grids, all vulnerable to solar storms. It's a humbling reminder that, however advanced our technology, we're still at the mercy of our star's moods. But there's something deeply comforting about this vulnerability. It connects us to the larger natural cycles of the cosmos, reminding us that we're part of a system much larger and older than our daily concerns. Every solar storm is a whisper from our star, a message that travels through the vacuum of space and finds echo in our machines and even in our bodies. Did you know that some studies suggest that geomagnetic storms can subtly affect human biological rhythms? While it's still an active area of research, there's evidence that changes in Earth's magnetic field during solar storms can influence everything from sleep patterns to the incidence of certain medical conditions. It's as if we were biological instruments subtly tuned by the electromagnetic music of the cosmos. Solar storms also provide us with natural laboratories for studying how charged particles interact with planetary magnetic fields and atmospheres. These interactions are similar to processes that occur around other planets in our solar system and around other stars throughout the galaxy. Understanding solar storms helps us understand fundamental plasma physics that governs much of the visible universe. The aurora displays created by solar storms have inspired human cultures for millennia. Indigenous peoples of the Arctic developed rich mythologies to explain these dancing lights. Some saw them as spirits of the dead, others as cosmic hunters pursuing celestial prey across the sky. These stories, while not scientifically accurate, captured the awe and wonder that auroras continue to inspire in people today. Modern solar storm forecasting has become a sophisticated science, combining observations from ground-based telescopes, space-based satellites, and computer models that simulate the complex interactions between the solar wind and Earth's magnetosphere. Scientists can now predict when a solar storm will arrive at Earth and estimate its potential impacts on technology and climate. But solar storms remain inherently unpredictable in their fine details. Our sun is a chaotic system where small changes can lead to dramatically different outcomes. A slight variation in magnetic field configuration can mean the difference between a minor geomagnetic disturbance and a major space weather event. This unpredictability adds an element of cosmic mystery to our relationship with our star. Just as we can't predict exactly when or lightning will strike during a thunderstorm, we can't predict exactly when the sun will unleash its most powerful magnetic eruptions in our direction. Now, my dear listener, let's dive, literally, into one of the most fascinating aspects of solar influence on our climate: the role of oceans as immense thermal memory banks. If the atmosphere is our planet's nervous system, responding quickly to changes, the oceans are its long-term memory, storing and releasing solar energy over decades and even centuries. Imagine the oceans as a liquid library where each water molecule carries the history of past interactions with solar radiation. When the sun heats the ocean surface, this energy doesn't disappear instantly. Water has an extraordinarily high heat capacity, much higher than air or land. This means the oceans can absorb enormous amounts of solar energy without dramatically increasing their temperature. To give you an idea of this magnitude, the first 10 feet of the ocean store as much thermal energy as the entire Earth's atmosphere. It's as if every cubic meter of seawater were a giant solar battery, storing energy that can be released slowly over time. But oceans aren't homogeneous. Solar radiation heats mainly their surface layers, creating a complex thermal stratification. In tropical regions, where the sun strikes most directly, there can be a difference of more than 36 degrees Fahrenheit between the surface and deep waters, just a few hundred meters down. This temperature difference drives ocean currents that function as a planetary circulatory system. The Antarctic Circumpolar Current, for example, is the largest ocean current in the world, transporting 150 times more water than all of Earth's rivers combined. This current connects the Atlantic, Pacific, and Indian Oceans, redistributing thermal energy accumulated by the sun in different regions of the planet. It's an underwater river of continental proportions, ultimately driven by energy from our star. And there's something almost magical about how oceans breathe solar energy. During the day, they absorb radiation. During the night, they release heat to the atmosphere, moderating temperatures. During summer, they store energy. During winter, they release it gradually. This is why coastal regions have more moderate climates than continental regions, oceans, function as gigantic natural thermostats. Have you ever walked on the beach during a summer night and felt how the air was still warm even hours after sunset? That's the ocean slowly releasing the solar energy it absorbed during the day. Its water molecules, agitated by solar heat, are gradually transferring this energy to the night air, creating the comforting sensation of persistent warmth. But perhaps the most fascinating aspect is how oceans function as a climatic time machine. Deep ocean waters, especially in polar regions, can take hundreds or even thousands of years to circulate completely around the globe. This means the water you might touch on a tropical beach could carry the thermal memory of solar energy absorbed when your great-great-grandparents were young. This long-term oceanic circulation is crucial for Earth's climate stability. It transports not just heat, but also dissolved gases like CO2 and oxygen. The oceans absorb about a quarter of all the CO2 we emit into the atmosphere, and this absorption is modulated by water temperature, which, in turn, is determined by solar radiation. There are regions of the oceans where surface waters, cooled and made denser by contact with polar air, sink to the depths, taking with them dissolved CO2 and oxygen. Other regions, especially near the equator, experience upwelling, where deep waters rich in nutrients but poor in oxygen rise to the surface. This entire vertical circulation system is driven by temperature differences created by unequal distribution of solar energy. And what about oceanic climate patterns like El Niño and La Niña? These phenomena, which can affect global climate for years, are fundamentally the result of interaction between solar energy and Pacific tropical waters. During an El Niño event, surface waters abnormally heated by the sun spread across the central and eastern Pacific, altering precipitation patterns worldwide. During La Niña, the pattern reverses, with cooler waters dominating the region. It's impressive to think that solar energy absorbed by Pacific tropical oceans can determine whether there will be drought in the Amazon, floods in California, or harsh winters in Europe. It's a powerful demonstration of how our star, through oceanic mediation, climatically connects all regions of the planet. The thermal inertia of oceans also explains why climate change doesn't happen instantaneously when atmospheric composition changes. Even if we stopped all greenhouse gas emissions tomorrow, the oceans would continue slowly releasing the excess heat they've absorbed over recent decades. It's like a massive thermal flywheel that keeps spinning long after the force that set it in motion has stopped. Ocean currents also transport heat through what scientists call the global conveyor belt circulation. Warm surface waters flow from the tropics toward the poles, gradually cooling and eventually sinking in polar regions. These cold waters then flow back toward the equator at depth, completing a circulation pattern that can take 1,000 years to complete one full cycle. This oceanic conveyor belt is sensitive to changes in temperature and salinity, both of which are influenced by solar energy. Too much fresh water from melting ice can slow down the circulation. Changes in evaporation patterns due to altered solar heating can change salinity. These changes in ocean circulation can have profound effects on regional and global climate patterns. The oceans also play a crucial role in the global carbon cycle, absorbing CO2 from the atmosphere when they're cool and releasing it when they're warm. This means that changes in ocean temperature due to variations in solar heating can affect atmospheric CO2 concentrations, creating a feedback loop between solar energy, ocean temperature, atmospheric composition, and climate. Marine life also plays a role in how oceans interact with solar energy. Phytoplankton near the surface absorb solar energy for photosynthesis, producing oxygen and consuming CO2. When these organisms die, Some sink to the ocean depths, effectively transporting carbon from the atmosphere to the deep ocean. This biological pump is another way that solar energy influences the global carbon cycle. So the next time you look at the sea, remember, you're contemplating the planet's largest archive of solar energy, a liquid library that stores decades of stellar radiation and slowly redistributes it around the globe, moderating our climate and making life on Earth possible. Take another deep breath, my dear journey companion. Feel the oxygen filling your lungs, feeding every cell in your body. Now imagine that every molecule of that oxygen was a direct gift from the sun, processed and offered to you by the world's forest through the miracle of photosynthesis. Photosynthesis is perhaps the most important process connecting solar energy to Earth's climate and life as we know it. It's a biological alchemy where sunlight, water, and carbon dioxide transform into sugar and oxygen. But this simple chemical description doesn't do justice to the elegance and complexity of this process that literally sculpts our climate. Imagine a leaf as a tiny biological solar power plant. Each leaf contains millions of chloroplasts, small green organelles that capture solar photons with an efficiency that makes our best solar panels envious. When a photon hits a chlorophyll molecule, electrons are energized and begin a cascade of reactions that culminates in glucose production and oxygen release. But photosynthesis isn't just about producing food and oxygen. It's a fundamental mechanism of climate regulation. Plants absorb CO2 from the atmosphere during photosynthesis, removing one of the main greenhouse gases from the air. It's estimated that terrestrial plants absorb about 120 billion tons of carbon per year, approximately 6 times more than all annual human emissions. Have you ever walked through a forest on a sunny day and felt how the air seemed fresher and more humid? That's not just a romantic impression. Trees are literally modifying the microclimate around them through processes driven by solar energy. During photosynthesis, plants absorb water from the soil through their roots and transport it to their leaves. There, part of this water evaporates through stomata, tiny pores in leaves, in a process called transpiration. A single large tree can transpire hundreds of gallons of water per day, creating a local cooling effect. It's as if each tree were a natural air conditioner powered by solar energy. On a larger scale, entire forests can influence regional precipitation patterns. Water transpired by plants becomes vapor in the atmosphere, which can condense into clouds and precipitate as rain, often over the forest itself. The Amazon is a spectacular example of this phenomenon. This vast tropical forest doesn't just receive rain, it creates it. Through transpiration powered by intense equatorial solar radiation, the Amazon launches more than 20 billion tons of water into the atmosphere daily. This water forms the so-called flying rivers, atmospheric currents of water vapor that transport moisture from the Amazon basin to other regions of South America. Without solar energy driving Amazonian photosynthesis and transpiration, regions like southern Brazil, Uruguay, and northern Argentina could have much more arid climates. It's a powerful demonstration of how energy from our star, channeled through plants, can influence continental climate. And there's yet another fascinating aspect. The rhythm of photosynthesis varies seasonally as solar energy availability changes. In the northern hemisphere, during spring and summer, when days are long and the sun is high in the sky, photosynthesis intensifies dramatically. Billions of plants awaken from their winter dormancy and begin absorbing CO2 from the atmosphere at an accelerated pace. This creates a measurable seasonal oscillation in atmospheric CO2 concentrations. It's as if the entire planet were breathing. During boreal spring and summer growth, CO2 concentrations decrease as plants absorb it. During autumn and winter, when photosynthesis diminishes and organic matter decomposition continues, concentrations increase again. You can think of forests as immense planetary lungs that breathe to the rhythm of the seasons, modulated by solar energy. And this respiratory rhythm of forests has a cascading effect on global climate. More CO2 absorption means less greenhouse warming. More transpiration means more atmospheric moisture and potential for cloud formation. But there's an additional complexity. Forests don't just respond to solar climate. They also modify it through their albedo. Forests are generally darker than other surfaces, absorbing more solar radiation. This can create a local warming effect. At the same time, through transpiration and cloud formation, they can create a cooling effect. The net result of this interaction between radiation absorption and evaporative cooling varies depending on latitude, forest type, and season. It's a complex dance between life, light, and climate. Each leaf swaying in the breeze is a small solar laboratory where energy from our star transforms into life, oxygen, and climate regulation. Each forest is a green symphony orchestrated by sunlight, playing a melody that resonates in global climate. Forests also influence climate through their role in the carbon cycle. Trees not only absorb CO2 during photosynthesis, but also store carbon in their wood, roots, and in forest soils. Old-growth forests can store enormous amounts of carbon accumulated over centuries of solar-powered growth. When forests are cut or burned, this stored carbon is released back to the atmosphere as CO2. The seasonal cycle of forest photosynthesis also affects other atmospheric gases. During the growing season, increased photosynthesis means increased production of volatile organic compounds by plants. These compounds can react with other atmospheric chemicals to form particles that can serve as cloud condensation nuclei, potentially increasing cloud formation and affecting climate. Different types of forests have different relationships with solar energy and climate. Tropical rainforests with intense year-round solar radiation maintain high rates of photosynthesis and transpiration throughout the year. Temperate deciduous forests have dramatic seasonal variations in their solar energy utilization, with most photosynthetic activity concentrated in the months when leaves are present. Boreal forests, adapted to high latitudes with extreme seasonal variations in daylight, have evolved strategies to maximize their use of the limited solar energy available during their short growing seasons. The relationship between forests and solar energy also varies with forest age and structure. Young, rapidly growing forests absorb CO2 at higher rates than old, mature forests. But mature forests often have more complex canopy structures that create diverse microclimates and support greater biodiversity. The interactions between forest structure and solar energy influence everything from local weather patterns to wildlife habitat. Climate change is altering these forest-solar energy relationships in complex ways. Changes in temperature and precipitation patterns are shifting the boundaries of different forest types. Some forests are experiencing increased growth due to longer growing seasons and higher CO2 concentrations, while others are stressed by droughts, heat waves, and changing precipitation patterns. So when you breathe again, remember, you're inhaling the direct product of solar energy processed by plants. You're participating in a cycle that connects your lungs to tree leaves, to ocean plants, and ultimately to nuclear fusion in the core of our star. It's a chain of connections that goes from the heart of the sun to the center of your being. Now, my dear knowledge traveler, let's direct our attention to some of the most majestic and climatically crucial manifestations of the interaction between solar energy and our planet, glaciers and polar ice caps. These immense masses of ice are much more than spectacular landscapes. They're fundamental climate regulators that function as giant mirrors reflecting solar energy back to space. Imagine you're flying over Greenland or Antarctica. Below you stretches a white ocean of ice that seems infinite, a surface so bright it hurts your eyes even through airplane windows. This whiteness isn't just aesthetically impressive, it's climatically crucial. Ice and snow have a very high albedo, meaning they reflect between 80% and 90% of the solar radiation they receive back to space. To put this in perspective, while a dark ocean can absorb more than 90% of the solar energy that hits it, an icy surface reflects almost all of that energy. It's a difference that might seem subtle, but has profound climate consequences. Polar regions function as immense planetary refrigerators, not just because they receive less solar energy due to the angle of incoming rays, but also because they efficiently reflect the energy they do receive. Have you ever wondered why Earth's poles are white? It's a deeper question than it appears. Ice forms because polar temperatures are below water's freezing point, and these low temperatures exist because these regions receive less direct solar energy. But once ice forms, it creates a feedback cycle. Its high reflectivity keeps the region cool, preserving more ice, which in turn reflects more solar radiation. It's a perfect example of what climate scientists call positive feedback. But Positive here doesn't mean good, just that the effect reinforces itself. More ice leads to more reflection, which leads to more cooling, which leads to more ice. Conversely, if ice begins to melt, it exposes darker surfaces, ocean or land, that absorb more solar energy, causing more warming and more melting. This ice-albedo feedback mechanism is one of the reasons polar regions are considered some of the most sensitive places to global climate changes. Small changes in average temperature can trigger large changes in ice cover, which in turn amplify those temperature changes. Glaciers are extraordinary climate archives. Each layer of ice that forms annually preserves a sample of that year's atmosphere, including bubbles of ancient air. By drilling deep into the ice caps of Greenland and Antarctica, scientists can reconstruct Earth's climate history over hundreds of thousands of years. It's like reading a book written by the atmosphere itself, page by page, year by year. These glaciers tell us fascinating stories about how solar energy has varied in the past and how climate responded. They reveal periods when the planet was much colder, with vast ice sheets covering much of North America and Europe. They also reveal warmer periods, when sea levels were meters higher than today. But glaciers aren't just passive archives, they're active participants in the climate system. When they slowly move toward the ocean, they carry with them freshwater ice that, when it melts, can alter the salinity and density of ocean waters. This can influence ocean currents, which in turn affect global climate patterns. The North Atlantic Current, for example, which keeps Western Europe relatively warm, is partially driven by the formation of dense, salty water in the North Atlantic. If large amounts of fresh water from Greenland glaciers entered the ocean, they could alter this circulation, potentially cooling Europe even in a globally warming world. Did you know that glaciers also influence climate through their topography? The great ice sheets of Greenland and Antarctica are so massive, some more than 2 miles thick, that they create their own microclimates. Air flowing over these vast expanses of ice cools and descends, creating katabatic winds that can reach hurricane speeds. These icy winds don't just affect local climate, but also influence global atmospheric circulation. It's as if glaciers were gigantic wind-making machines, powered indirectly by the solar energy that determines their temperature and stability. And there's something almost poetic about how glaciers respond to seasonal changes in solar energy. During polar summer, when the sun doesn't set for months, glacier surfaces can melt slightly, creating temporary lakes of liquid water over the ice. During polar winter, when the sun doesn't rise for months, these regions become some of the coldest places on Earth. Glaciers are, in many ways, the planet's thermometers. They respond sensitively and visibly to changes in the amount of solar energy the planet retains versus the amount it reflects back to space. When this balance changes, whether due to variations in solar activity, changes in atmospheric composition, or other factors, glaciers respond by growing or shrinking. The seasonal cycle also affects glacier behavior in complex ways. During summer, increased solar heating can create meltwater that flows to the base of glaciers, potentially lubricating their movement and causing them to flow faster toward the ocean. During winter, this lubrication effect diminishes and glacier flow typically slows. Glaciers also play a crucial role in global sea level. The great ice sheets of Greenland and Antarctica contain enough ice to raise global sea levels by more than 200 feet if completely melted. While such complete melting would take many centuries or millennia, even small changes in these ice sheets can have significant impacts on coastal regions around the world. The relationship between glaciers and solar energy is also mediated by clouds and atmospheric moisture. In some regions, increased warming can lead to more evaporation and cloud formation, which can actually increase snowfall on glaciers. In other regions, warming leads to more rain instead of snow, reducing glacier accumulation. Glacial ice also affects the local and regional radiation balance through its interactions with solar energy. Fresh snow can reflect up to 90% of incoming solar radiation, but as snow ages and accumulates dust and other particles, its reflectivity decreases. Glacial ice, which is denser and often contains bubbles and impurities, typically reflects somewhat less solar radiation than fresh snow. The timing of seasonal snowmelt is also crucial for regional climate and water resources. Earlier melting due to increased spring solar heating can affect river flows, groundwater recharge, and the availability of water for agriculture and municipal uses. Changes in snowmelt timing can also affect plant and animal communities that have evolved to synchronize their life cycles with traditional patterns of water availability. So when you think about polar regions, remember, they're not just remote, icy landscapes. They're active components of the global climate system, giant mirrors that reflect solar energy, archives of climate history, and sensitive indicators of changes in the planet's energy balance. Every ice crystal in these vast white expanses is a testament to the ongoing dance between our star and our world. Now we arrive, my dear listener, at one of the most complex and contemporary chapters of our journey, the relationship between modern climate change and solar influence. It's a story that requires nuance, scientific precision, and a careful understanding of multiple variables that interact in sometimes surprising ways. You've certainly heard debates about global warming and climate change, and you may have wondered, if the sun is the main driver of Earth's climate, wouldn't it be natural for changes in solar activity to be the primary cause of the climate changes we observe? It's a perfectly logical question, and the answer takes us through some of the most sophisticated scientific research ever conducted. First, let's establish the facts about recent solar changes. Since we began precisely measuring solar radiation with satellites starting in the 1970s, we've observed that the total energy the sun emits varies slightly. These variations mainly follow the 11-year sunspot cycle we discussed earlier, with changes of approximately 0.1% between solar maximum and minimum. To put this in perspective, 0.1% might seem like a tiny amount, but in terms of global energy, it represents about 1.4 watts per square meter difference in radiation hitting the top of our atmosphere. For comparison, the additional greenhouse effect caused by CO2 we've added to the atmosphere since pre-industrial times is approximately 2 watts per square meter, about 40% larger than the maximum solar variation. But here's the most intriguing aspect. If we look at long-term trends in solar activity over recent decades, they don't match the observed global warming trends. In fact, since the 1980s, solar activity has shown a slight downward trend, while global temperatures have continued rising consistently. This doesn't mean the sun has no influence on modern climate. It certainly does. But it means other factors have become dominant. It's like an orchestra where the sun has always been the conductor, but now other instruments are playing so loudly they're beginning to drown out the solar melody. The main one of these other instruments is greenhouse gases added to the atmosphere by human activity. CO2, methane, nitrous oxide, and other gases fundamentally alter how our atmosphere interacts with solar radiation. They allow solar radiation to enter relatively easily, but make it difficult for infrared radiation emitted by Earth to escape back to space. It's important to understand that this greenhouse effect isn't inherently bad. In fact, it's what makes our planet habitable. Without natural greenhouse gases, Earth would be about 60 degrees Fahrenheit colder, a frozen world where complex life would be impossible. The problem arises when the concentration of these gases changes rapidly, altering the energy balance that sustains our climate. Have you ever wondered how scientists can separate solar influence from human influences on climate? It's one of the most sophisticated challenges in climate science. They use a combination of instrumental records, proxy data, like tree rings and ice cores, complex climate models, and a detailed understanding of the physical mechanisms involved. One of the most convincing pieces of evidence comes from the stratosphere, the atmospheric layer between 6 and 30 miles altitude. If global warming were caused primarily by changes in solar energy, both the surface and stratosphere should be warming. But what we observe is the opposite. The surface is warming while the stratosphere is cooling. This is exactly what we'd expect if warming were caused by increased greenhouse gases, which trap heat near the surface. There's also fascinating evidence from carbon isotope analysis. CO2 from fossil fuel sources has a slightly different isotopic signature than CO2 from natural sources. By measuring these proportions in the atmosphere, scientists can determine that the increase in atmospheric CO2 comes predominantly from burning fossil fuels, not from natural processes, but this doesn't mean we should ignore solar influence. The sun continues to be the fundamental driver of the climate system, and long-term solar variations can still have significant effects. There's evidence that solar activity changes contributed to historical climate events like the Little Ice Age between the 14th and 19th centuries. Moreover, solar influence can be amplified by complex feedback mechanisms. Small changes in solar radiation can trigger larger changes in atmospheric and oceanic circulation patterns. It's like a small stone that, rolling down a mountain, can trigger an avalanche. There are also aspects of solar variability that we don't yet fully understand. The sun's ultraviolet radiation varies more in percentage terms than total radiation during the solar cycle. This UV variation can affect stratospheric chemistry and potentially influence climate patterns in subtle but significant ways. And then there's the question of future predictions. If solar activity decreases significantly in coming decades, as some scientists suggest it might, could this partially moderate global warming caused by greenhouse gases? It's an active area of research, but most studies suggest that even a significant solar decrease would be insufficient to offset expected warming from human emissions. The story of modern climate change is therefore a story of multiple influences. The sun continues to be the fundamental protagonist, providing the energy that drives the entire system. But humans have become a new major character, rapidly altering how the planet responds to solar energy. It's a profound responsibility and a unique opportunity in planetary history. For the first time, a species has the knowledge and capability to understand and potentially influence global climate. The question that remains is, what will we do with this knowledge and responsibility? Climate scientists have developed increasingly sophisticated methods for studying solar-climate relationships. They use networks of ground-based solar observatories, satellite measurements of solar radiation, and detailed records of solar activity going back centuries. They've also developed complex computer models that can simulate how different factors, solar variations, greenhouse gas concentrations, volcanic eruptions, land use changes, interact to influence climate. These models have been tested against historical climate data and have successfully reproduced many observed climate changes. When the models include only natural factors like solar variations and volcanic eruptions, they cannot explain the rapid warming observed since the mid-20th century. But when human factors are included, the models closely match observed temperature trends. The relationship between solar activity and climate is also complicated by regional variations. While global average temperatures are the most commonly discussed metric, climate change affects different regions differently. Some areas warm more than others, some experience changes in precipitation patterns, and some see shifts in the timing of seasons. Solar variations can also affect regional climate patterns through their influence on large-scale, atmospheric circulation systems. For example, changes in solar UV radiation can affect the temperature and ozone concentration in the stratosphere, which can in turn influence the jet stream and storm tracks in the troposphere. Understanding these regional effects of solar variability is important for predicting how future changes in solar activity might interact with ongoing climate change from greenhouse gas emissions. While solar effects alone cannot explain recent global warming, they may still play a role in determining regional climate patterns and the timing of climate changes. Here we are, my dear reflection companion, facing one of the most hopeful and practical applications of our understanding of the relationship between the sun and climate: solar technology. After exploring how our star naturally governs Earth's climate system, it's deeply appropriate to consider how we can consciously harness this same energy to create a more sustainable future. Imagine for a moment the poetic elegance of this, using solar energy, the same force that drives winds, ocean currents, and the water cycle, to power our cities, homes, and vehicles. It's as if we were learning to dance in harmony with the cosmic rhythm that already governs our planet, rather than fighting against it. Modern solar technology is truly a marvel of human engineering. Today's photovoltaic panels can directly convert sunlight into electricity through the photoelectric effect, the same physical phenomenon for which Einstein won the Nobel Prize. When solar photons hit certain semiconductor surfaces, they release electrons, creating an electrical current. It's an almost magical transformation, pure light becoming usable energy. Did you know that in just 1 hour, the sun provides Earth with more energy than all of humanity consumes in an entire year? It's a statistic that always amazes me. Theoretically, if we could capture just a tiny fraction of the solar energy hitting our planet, we could meet all of human civilization's energy needs indefinitely. And technology is rapidly making this theoretical possibility a practical reality. The cost of solar energy has plummeted more than 90% in the last 2 decades. Solar panels that cost thousands of dollars in the 1980s now cost less than $100. It's a cost reduction that rivals the famous Moore's law for computers. But photovoltaic solar energy is just one way to harness our star. Solar thermal energy uses mirrors or lenses to concentrate solar radiation, heating fluids that generate steam to drive turbines. Some of these solar thermal plants can even store heat in molten salts, allowing them to generate electricity even hours after sunset. It's like capturing a bit of the sun itself and releasing it slowly as needed. And there are even more elegant and integrated applications. Passive solar architecture uses building positioning, orientation, and materials to naturally harness solar energy for heating, lighting, and ventilation. It's an approach that works with daily and seasonal patterns of solar radiation, creating spaces that are energy efficient by design, not through additional technology. Have you ever considered how your own home interacts with solar energy? Window orientation, wall colors, roof insulation, all these factors determine how much solar energy your house absorbs, reflects, or conserves. Even without solar panels, every building is essentially a passive solar collector, and small changes in design can have large impacts on energy consumption. There are also fascinating emerging technologies that mimic natural processes we observe in nature. Artificial photosynthesis, for example, tries to replicate what plants do naturally, use solar energy to split water molecules and produce hydrogen, which can be used as clean fuel. It's literally trying to learn from billions of years of evolution to create our own artificial leaves. And what about perovskite solar cells, which promise to be even more efficient and cheaper than traditional silicon? Or flexible solar panels that can be integrated into clothing, tents, or curved surfaces? Solar innovation is happening at an impressive pace, making it increasingly plausible to envision a future where solar energy is truly ubiquitous. But perhaps the most profound aspect of solar technology is how it can reconnect us with our planet's natural rhythms. Solar energy systems make us more aware of the amount of sunlight available at different seasons, times, and weather conditions. They make us think about energy storage during sunny periods for use during cloudy or nighttime periods. There's ancient wisdom in this, the same wisdom that plants developed over millions of years. They capture solar energy when it's available, store it in chemical form, and release it when needed. Our solar energy systems with batteries are essentially doing the same thing, just with technology instead of biology. And consider the climate impact. Every kilowatt hour of electricity generated by solar energy instead of fossil fuels represents CO2 that isn't emitted into the atmosphere. On a global scale, solar energy expansion is one of the most powerful tools we have for climate stabilization, reducing our dependence on fuels that alter atmospheric composition. It's ironic when you think about it. Fossil fuels are, ultimately, ancient solar energy, energy captured by plants and microorganisms over millions of years and buried underground. When we burn coal, oil, or natural gas, we're releasing at once solar energy that was slowly accumulated and stored geologically. Modern solar energy allows us to access stellar energy directly, in real time, without digging up the geological past. Have you ever imagined what a world totally powered by solar energy would look like? Cities where every roof is an energy collector, vehicles that charge while parked in the sun, farms that produce both food and electricity through agrivoltaic systems that combine agriculture and solar panels. It's not science fiction. Much of this technology already exists and is being implemented around the world. And there are benefits that go beyond simple energy generation. Distributed solar energy, panels on individual homes and businesses, can make the electrical system more resilient and democratic. Instead of depending on large, centralized power plants, communities can generate their own energy, share it among neighbors, and maintain energy independence during emergencies. There's something deeply empowering about generating your own energy from sunlight. It's a way of consciously participating in the same process that plants have used for eons, of connecting directly with the energy source that sustains all life on Earth. Solar technology also represents a form of climate adaptation. As weather patterns become more extreme due to climate change, having distributed, resilient energy systems becomes increasingly important. Solar energy can provide power during grid outages, reduce strain on centralized infrastructure, and help communities become more self-sufficient. The development of solar technology has also driven innovations in energy storage, smart grids, and energy management systems. These technologies are creating more efficient and flexible energy systems that can better integrate renewable energy sources and respond to changing demand patterns. But perhaps most importantly, widespread adoption of solar technology represents a conscious choice to align our energy systems with natural processes rather than working against them. It's a choice to power our civilization with the same energy that drives photosynthesis, ocean currents, and weather systems, the energy of our star. This alignment with natural energy flows has implications beyond just reducing greenhouse gas emissions. It represents a fundamentally different relationship with our environment, one based on working with natural systems rather than extracting resources from them. It's a step toward what some call a solar civilization, a form of human society that operates within the energy budget provided by our star. The economics of solar energy are also rapidly changing the global energy landscape. As solar becomes the cheapest form of electricity in many parts of the world, it's driving changes in energy markets, international trade, and geopolitics. Countries with abundant sunshine are becoming energy exporters, while traditional fossil fuel producers are adapting to a changing energy economy. Solar technology is also creating new opportunities for energy access in remote and developing regions. Off-grid solar systems can provide electricity to communities that have never been connected to centralized power grids, enabling everything from basic lighting to internet connectivity to refrigeration for vaccines and medicines. Now, my dear thought traveler, we arrive at a territory where science and philosophy meet, where data and numbers give way to deeper questions about our place in the cosmos and our responsibility as a conscious species on a planet that dances eternally with its star. Our entire journey so far, from solar radiation physics to climate system complexities, leads us to a fundamental realization: we are solar creatures. Every carbon atom in our body was forged in the core of a star. Every calorie of energy that fuels our thoughts originally came from nuclear fusion in our local star. Every breath we take is possible thanks to solar photosynthesis that produces oxygen. Have you ever stopped to truly contemplate this connection? Right now, as you process these words, neurons in your brain are firing using energy that traveled 93 million miles from the sun, was captured by plants through photosynthesis, passed through the food chain, was metabolized by your cells, and now powers the miracle of consciousness. You are literally organized starlight thinking about itself. This realization of our solar nature should, I believe, profoundly influence how we see our responsibility to the planet. If we are creatures shaped by stellar energy, living in a world where every climate process is a manifestation of that energy, then drastically altering climate systems isn't just a practical issue. It's an existential question about what it means to be human in a larger cosmos. The relationship between the sun and Earth's climate teaches us about interconnection, feedback, and balance. Small changes can have enormous cascading effects. Systems that appear separate are intimately connected. What happens in one part of the system affects all other parts. These aren't just lessons about meteorology, they're lessons about how to live consciously in a complex, interconnected world. Consider the elegance of the natural cycles we've explored. Water evaporating from oceans, forming clouds, falling as rain, flowing back to the sea. Carbon being absorbed by plants, released in respiration, circulating between atmosphere, biosphere, and oceans. These cycles have functioned for billions of years, driven by solar energy, maintaining conditions that allow life to flourish. And now, for the first time in our planet's history, one species, us, has developed the ability to consciously alter these global cycles. It's unprecedented power, and with it comes equally unprecedented responsibility. What kind of ancestors do we want to be for future generations? What kind of climate legacy do we want to leave? There's a beautiful paradox in this situation. The same intelligence that allows us to understand solar climate systems also gave us the power to perturb them. The same technology that brought us fossil fuels also brought us solar and wind energy. The same science that showed us our influence on climate also shows us paths to sustainability. Have you ever wondered if our species is going through a kind of cosmic adolescence? We've developed tremendous power and capabilities, but we're still learning to use them wisely. We're discovering that actions have consequences, that power comes with responsibility, that we need to think not just about the present, but about the long-term future. The solar perspective offers us a way of thinking about time that transcends our daily concerns. The sun has been shining for 4.6 billion years and will continue shining for another 5 billion. On what time scale should we think about our influence on climate? Decades? Centuries? Millennia? And there's a profound humility that comes from understanding our dependence on the sun. For all our technology and knowledge, we're still fundamentally dependent on energy from a star for our survival. If the sun varied significantly, or if our atmosphere changed drastically, all our civilization would be affected. We're powerful, but also vulnerable. But this vulnerability isn't weakness, it's a source of wisdom. It reminds us that we're part of something larger, that our prosperity is intimately linked to the health of natural systems, that our future depends on maintaining the delicate balance that allows life to flourish on Earth. Solar philosophy invites us to think as conscious inhabitants of a planet orbiting a star, not as owners of resources to exploit. It invites us to see climate systems as our partners and collaborators, not as forces to dominate. It invites us to consider our impact not just on the next fiscal quarter, but on the next generations, the next centuries. And perhaps more deeply, it invites us to rediscover a sense of reverence and wonder before the cosmos of which we're part. Every sunset is a reminder of our planet's rotation. Every seasonal change is a reminder of our orbital dance. Every ray of light touching our skin is a direct gift from our star. Living with solar consciousness is living with constant awareness of our participation in larger cosmic processes. It's choosing clean energy not just for practical reasons, but as a way of aligning our technology with the natural energy flows that sustain life. It's protecting forests not just for their biodiversity, but for their role as interfaces between solar energy and climate systems. It's thinking about our cities, our economies, our societies as parts of a larger system that includes atmosphere, oceans, biosphere, and ultimately our central star. It's recognizing that our prosperity and the prosperity of all other beings with whom we share this planet are inextricably linked to maintaining the natural systems that solar energy sustains. The solar perspective also offers a way of thinking about human potential that's both humbling and inspiring. We are the universe becoming conscious of itself. Stellar matter organized in such a way that it can contemplate its own origins and influence its own future. This consciousness brings both great power and great responsibility. Living with solar consciousness means recognizing that we're part of an ongoing cosmic story that began with the birth of our star and will continue long after our individual lives have ended. It means making choices based not just on immediate needs, but on our role as temporary stewards of a planetary system that's been evolving for billions of years. It means seeing our technologies not as separate from nature, but as extensions of natural processes. Solar panels that convert sunlight to electricity are mimicking photosynthesis. Wind turbines that capture moving air are harnessing atmospheric circulation driven by solar heating. These technologies represent humanity learning to work with natural energy flows rather than against them. The solar perspective also offers hope. Despite the challenges of climate change, we have an abundant, clean energy source that will continue shining for billions of years. We have the knowledge to understand how our actions affect climate systems. We have technologies that can help us live more sustainably. What we need is the wisdom and will to use these gifts responsibly. Perhaps most importantly, solar consciousness invites us to think beyond purely human concerns, to consider our responsibilities to all life on Earth. The same solar energy that sustains human civilization also sustains the forests. oceans, and countless other species that share our planet. Our choices about how to use solar energy affect not just human welfare, but the entire web of life of which we're part. This expanded sense of responsibility represents a kind of planetary consciousness, an awareness that we're not separate from the natural world but part of it, dependent on it and responsible to it. It's a consciousness that recognizes our power to influence planetary systems and commits to using that power wisely and ethically. And here we arrive, my dear journey companion, at the end of our exploration and the beginning of all the future possibilities that open before us. After traveling together through stellar physics, climate systems, solar technologies, and the philosophical implications of our solar condition, it's time to look forward and contemplate what might lie ahead. The future of the relationship between the Sun, Earth, and humanity will be shaped both by cosmic forces beyond our control and by choices we make every day. Our star will continue its stellar life cycle, burning hydrogen into helium for another few billion years. Earth's climate systems will continue their complex dance of feedbacks and interactions. And we, as a species, will continue evolving our understanding and our technology. But there are aspects of this future that we can actively influence. We're on the threshold of a possible energy revolution where solar energy becomes so cheap and ubiquitous that it fundamentally transforms our relationship with power and consumption. Imagine cities where every service captures solar energy, where transportation is powered by sunlight, where energy is so abundant and clean that energy scarcity becomes a thing of the past. This energy transition isn't just a technical matter, it's an opportunity to reimagine how we live on the planet. When our energy comes directly from the sun in real time, instead of fossil fuels extracted from the geological past, our relationship with time and natural cycles changes fundamentally. We become more attuned to daily and seasonal rhythms of energy availability. Can you imagine societies that consciously organize themselves around solar cycles? Cities that are more active during sunny days and more contemplative during cloudy periods? Economies that pulse to the rhythm of renewable energy availability? It's not romantic nostalgia. It's a possible more sustainable and harmonious form of civilization. And there are technological developments on the horizon that could further revolutionize our ability to harness solar energy. Solar cells that operate at near theoretical efficiency, storage systems that can hold seasonal energy, transmission technologies that can transport solar energy from the world's sunniest deserts to anywhere on the globe. There are even proposals for space-based solar collectors, enormous arrays of solar panels orbiting Earth, capturing solar energy without atmospheric interference and transmitting it to the surface via microwaves. It would be like having direct access to the sun 24 hours a day, regardless of weather or Earth's rotation. But perhaps the most transformative aspect of the solar future is how it might change our collective consciousness about our place in the cosmos. As we become more dependent on direct solar energy, we might rediscover a sense of connection with our star that our species hasn't felt since the times when we depended entirely on natural cycles for survival. This reconnection might come with greater awareness of other aspects of our cosmic dependence. Perhaps we'll develop deeper appreciation for lunar cycles that affect tides and some biological rhythms. Perhaps we'll become more conscious of our position in the galaxy and how distant cosmic events might subtly influence our planet. And there's the fascinating question of how our understanding of solar climate systems might help us understand and potentially inhabit other worlds. As we explore Mars, Venus, and the moons of giant planets, our experience with how stars shape planetary climates becomes practical knowledge for survival in extraterrestrial environments. Mars, for example, once had a denser atmosphere and warmer climate, possibly sustained by a more robust greenhouse effect. Understanding how the sun interacts with different types of planetary atmospheres helps us imagine how we might potentially terraform other worlds or build sustainable habitats on them. There's also the intriguing possibility that, as our technology advances, we might develop ways to slightly modulate our own absorption and reflection of solar energy for climate management purposes. Not changing the sun, but changing how our planet interacts with solar energy through technologies like space mirrors or modification of surface albedo. These possibilities raise deep ethical questions. If we have the power to consciously influence global climate through modification of our interaction with solar energy, what responsibilities does that bring us? Who decides how to use this power? How do we ensure that future generations inherit a climatically stable planet? And there's the deeper question of how our growing ability to influence planetary systems changes our identity as a species. We're becoming planetary gardeners, responsible not just for our own survival, but for maintaining conditions that allow all life to flourish on Earth. Perhaps the most hopeful future is one where we develop not just the technology to live sustainably with solar energy, but also the wisdom to do so in ways that honor our interdependence with all other life systems on the planet. A future where abundant, clean energy frees us not to consume more, but to live more consciously. A future where every child grows up knowing that the energy powering their home, school, and community comes directly from the same star that warms their face, makes plants grow, drives winds and ocean currents. A future where energy education is automatically education about astronomy, climatology, and our connection to the cosmos. And perhaps, as we become a truly solar civilization, we'll rediscover ancient wisdom about living in harmony with natural cycles, combining it with modern technologies to create ways of life that are simultaneously advanced and sustainable, powerful and humble, conscious of our ability to influence the world and our responsibility to do so wisely. The future of the Sun-Earth-humanity relationship is being written now in every energy choice we make, every climate policy we implement, every technology we develop. It's a future we can consciously shape to be more harmonious, more sustainable, and more conscious of our participation in the cosmic dance that connects our star, our planet, and all forms of life that call Earth home. Looking ahead, we can envision a world where understanding our solar connection becomes fundamental to education, where children learn about energy by understanding the journey of photons from the sun's core to their solar calculator, where weather prediction incorporates space weather from solar storms, where architecture is designed to work with solar angles and seasonal variations. We might develop new forms of art and culture inspired by our solar relationship, music that follows solar cycles, architecture that celebrates our stellar connection, literature that explores our place in the cosmic energy web. Our relationship with the sun could become a source of cultural renaissance as well as technological revolution. The integration of solar technology with artificial intelligence and smart systems could create energy networks that automatically optimize themselves based on solar availability, weather patterns, and usage demands. Our energy systems could become as responsive and adaptive as natural ecosystems. Climate science will continue advancing our understanding of solar-climate interactions, potentially revealing new mechanisms by which solar variations influence weather patterns. This knowledge could improve our ability to predict both natural climate variations and the effects of human activities. International cooperation on solar energy could become a new form of diplomacy, with countries sharing solar technology and forming new alliances based on clean energy development rather than fossil fuel resources. The abundance of solar energy could help reduce resource conflicts and promote global cooperation. As we develop these technologies and deepen our understanding, we're not just solving energy and climate challenges, we're evolving our relationship with the natural world and our place in the cosmos. We're learning to be conscious participants in the great cycles of energy and matter that connect us to our star and to all life on Earth. The future we create will depend on our wisdom in using the knowledge and power we're gaining. Will we use our understanding of solar climate systems to create a more sustainable and equitable world? Will we develop technologies that work with natural processes rather than against them? Will we remember our cosmic connections as we reshape our civilization? These are the questions that will define the next chapter in the relationship between the sun, Earth, and humanity. And the answers will be written by all of us, and the choices we make today and every day going forward. And now, my dear listener, we've reached the end of our journey together through the intimate and complex relationship between the sun and our planet's climate. We've explored how our star governs every aspect of weather and climate patterns, from the formation of a single cloud to the great ocean currents that redistribute heat around the globe. We've seen how we are creatures literally made of starlight, dependent at every moment on solar energy for our survival. connected through invisible chains of causation to nuclear processes in our star's heart. We've discovered how small variations in solar activity can influence Earth's climate, and how our own activity as a species has become a climate force comparable to natural solar variations. We've contemplated the technological and philosophical possibilities that emerge when we deeply understand our solar nature, and how this understanding can guide us toward a more sustainable and conscious future. I hope this journey has awakened in you a renewed sense of wonder at the elegance of the natural systems that sustain us, and perhaps a deeper appreciation for the complex beauty of the dance between our star and our world. Thank you for accompanying me on this exploration. May you carry with you this solar consciousness, always remembering our participation in the great cosmic cycles that connect us to something infinitely larger than ourselves. And I leave you with this final question for your contemplation. If we now know so much about how the sun influences our climate, and if we have growing power to influence this system ourselves, to what extent do we truly know and control the real origins of the climate changes we face? And what responsibility does this understanding bring for the future we choose to create?